Homework 3.4, the rational zero theorem, zeros of polynomial functions. Video 4, homework due Wednesday, May 27th, 2020 at 11:59 p.m. And you may notice that where it says try homework 3.4, it's the same numbers that were in the parentheses in the previous video, meaning that what you're about to see is what these problems are asking you to do. The reason they were listed in the previous video in parentheses is because they ask you to list possible rational zeros, and then do something more. So how do you apply the rational zero theorem? Well, remember the whole problem with finding zeros of a polynomial function is we have to find a division problem whose remainder is zero. But what are we supposed to divide by? What's supposed to go in the box in synthetic division? If I don't tell you that, then you have to make an educated guess. And that's what the possible rational zeros are. The possible rational zeros are box numbers that could possibly give a remainder of zero. All right, so this problem is going to ask us to do three things. Part A, list all the possible rational zeros. Part B, use synthetic division to locate an actual zero. And then part C, find all remaining zeros. Remember, this list are things that might be zeros, and then we actually have to figure out which one is. So, let's attack it. If you're ever asked to list all possible rational zeros, you always start with factors of the constant term on top and factors of the leading coefficient on the bottom. I'm going to abbreviate leading coefficient LC. Now this list will have a plus minus in front of it, but this one's going to be a lot shorter list. Which term is the constant term in this function? It's the one without the x. 2. So on the top we need to list factors of 2. There's only 2 of them, 1 and 2. And what's the leading coefficient? It's also 2. So the denominator is also just 1 and 2. This won't be nearly as many as fractions, and that's good. So let's make all of our possible fractions starting with over 1. 1 over 1 is 1. Don't forget the plus minus. Actually, I'm going to write them separately. You'll see why in a minute. Let's do all, we're not done with the over 1s. 1 over 1 is 1, so either 1 or negative 1. 2 over 1 is 2, so either 2 or negative 2. And now let's do the over 2s. 1 over 2 is 1/2, so 1/2 or negative 1/2. And 2 over 2 reduces to 1, which is already in the list. So we only have 6 numbers that might work. Good. I've seen problems where that list has 3 dozen numbers, and one of them might work. So there's our list of possible rational zeros. Now, if you need to write them all out like we did in the previous video and then clean them up, that's what you do. But you can do it more efficiently by not putting the 1 on the bottom when you're doing the over 1s, and any other fraction, if it reduces, don't write it. But the reason I split the plus minus is because of part B. We're going to find which of these gives a 0 when we use it as a box number in synthetic division. So why did I separate them? Because if one of them fails, we're going to cross it out. And if the plus minus are on top of each other, we can't cross out only one of them. So now it's the trial and error. Now we're going to set up a synthetic division problem where the coefficients of the function are the top row. So I already messed up there. So the top row is 2, 5, 6, and 2. But what do we put in the box? Well, one of these. Which one? Doesn't matter. We're going to have to keep going until we find one that gives us a remainder of 0. So pick a number, put it in the box, and cross your fingers. Most people will start with 1. I don't blame them. And this is why you need to be efficient with synthetic division. At the most, we're going to have to do 6 synthetic division problems. Hope it doesn't take you too long. I will remind you that when you do synthetic division, you start in the first column and add, then you multiply diagonally by the box number into the next column, and then you just add, multiply, until you get to the end. For example, on this one, add the first column, you get 2. 2 times 1 is 2. Add the next column, you get 7. 7 times 1 is 7. I can tell this isn't going to work. The minute you know it's not going to work, shut it down, but I'll finish it. Add to get 13. 13 times 1 is 13. Finally, add to get 15. This is not 0. The 1 is not the one. You are not the 0 we're looking for. 1 down, 5 to go. I'm going to leave this one up here just for posterior, just for the sake of having it up there. Let's try -1. Nobody said you have to do them in this order. You can jump around. If you want to try 2 next, that's fine. But let's try -1. In fact, the 2 has no chance of working, nor does the 1/2. Don't worry, in the next video I'll explain why. Let's try -1. All right, add to get 2, multiply by the box number to get -2. Add to get 3, multiply the box number to get -3. Add to get 3, multiply by the box number to get -3. Oh, so close. Add to get -1. But this is not 0 either, and this is starting to get a little angering because I just did a synthetic division problem, and the only thing it lets me do is cross out this number that didn't work. So let's try another. Now, I could go through all 6 of them until we find the one that works. But I'm not even going to try the 2, and I'll tell you why. In the next video, we'll make this more formal. The 1 never had a chance of working. Look at the function. Everything in it is positive. How can you expect to put a positive number in, do adding and multiplying with positive numbers, and end up with 0? You can't. No positive number will make this 0, so I'm not even going to mess with 2. Try it if you want. You won't get a remainder of 0. You get a very big positive number. And for the same reason, the 1/2 won't work either. I know it's a fraction, but it's positive. Putting a positive here, here, and here, and here keeps everything positive. No way stuff can cancel and give me a 0. Again, in the next video, we'll make that more formal, but if you just want a real quick hint, if every coefficient is positive, then the 0 can't be. So we're down to 2 numbers. Let's try -2. 2, 5, 6, and 2. Add to get 2, multiply to get -4, add to get 1, multiply to get -2, add to get 4, well this isn't going to work, multiply to get -8, and add to get -6. Bigger angry face because I've just done 3 synthetic division problems, and all they told me is I chose poorly. Well, it better be the -1/2, but honestly there's no guarantee it would be, except I set it up so that it will be. Because this list of possible rational zeros only says if there is a rational 0, it's in this list. If there's a rational 0. Oh no, -1/2 in the box. Run screaming with your hands waving in the air because fractions are scary. No, don't do that. Actually, 1/2 is the easiest fraction to deal with. Multiplying something by half means you cut it in half. And multiplying by a negative means that you change the sign. So as I multiply, instead of saying times -1/2, I'm going to say cut it in half, change the sign. Add to get 2, cut it in half, change the sign. That was easy. Add to get 4, cut it in half, change the sign. Good. Add to get 4, this is looking promising, cut it in half, change the sign, remainder is 0, I'm happy, smiley face there. So what does this mean? This means, one second folks, I'm going to write the answer to the possible rational zeros. There are ±1, ±2, and ±1/2. So what does it mean when we run a number through synthetic division and the remainder is 0? In the context of zeros of a function, it means this is one of them. So, x equals -1/2 is a 0 of f of x. Don't believe me? Substitute it. Oh wait, we don't have to. Remember the remainder theorem? The remainder theorem says if you want to put a number into a function to get the value, alternatively, you can put it into the box and the remainder is the value. So for example, if we put 1 into that function, we get 15. If we put -1 in, we get -1. And if we put in -2, we get -6. So these synthetic division problems aren't completely useless. They do tell us functional values. That's f of 1 because of the remainder theorem. That's f of -1 for the same reason. And -6 is f of -2. So there's some information, it's just not the information we're looking for. Okay, so we found a 0. That's great. So what does that get us? Well, I'm going to erase all the synthetic division problems that weren't the ones we were looking for. And we'll keep the one that we did because we're about to use it. Because part C says, all right, you found a 0. Now go find the rest of them. But that was the only one that worked. That was the only rational 0 that worked. For part C, this is where you actually use what the synthetic division problem tells you. Because remember, we did a division problem. We divided this by something and got a quotient. If you have a synthetic division problem whose remainder is 0, the box number can tell you one factor. Remember this factor theorem. If this is a 0, then x minus that is a factor, or x plus 1/2. So the box number can go back into being the divisor. And the bottom row can go back into being a quotient, which would be the other factor. Just remember, when you actually do a division problem synthetically, the degree of the quotient is 1 less than the degree of the dividend. So if this were a third degree polynomial, then this represents a second degree polynomial. We start with x squared. So 2x squared plus 4x plus 4. That's the advantage to having a remainder of 0. You get 2 factors. One, by taking the 0 in the box and turning it back into a factor, and 2, by taking the quotient and turning it back into a polynomial. What I'm about to do is not necessary, but I just want to show you that we can clean this up a little bit. In a previous video, I mentioned that if your 0 is a fraction, then you could artificially multiply. Not if you're actually factoring. This is the correct factorization. I can't just walk up and give this a 2 out of nowhere. It would alter the value of the function. But what do you notice about this factor? Doesn't it have a GCF of 2? So if we factored a 2 out of this, we'd cut it down to x squared plus 2x plus 2. And if I distribute that 2 over here, it would give us 2x plus 1. So we actually can factor it using integers only, even though the 0 was not an integer, because the other factor had a GCF capable of eliminating that rational number over there. All right, but anyway, we're being asked to find the remaining zeros. And remember, when you're finding zeros, you're just solving a function equal to 0. Well, we already know what this one's going to give us. We technically don't have to do this because we already knew that -1/2 was a 0. But this guy needs some work. You can try to factor it, but I'll tell you right now it won't. If you're going to solve this one, you're going to either have to use completing the square or the quadratic formula. I'm thinking most of you would use the quadratic formula. I wouldn't, but I'll do the quadratic formula. So x equals -b, so -2, plus or minus a square root, we'll get back to that in a second, over 2a, so 2 times 1 is 2. Underneath here is b squared, so 2 squared, minus 4 times a times c, so 4 times 1 times 2. That's 4, that's 8, 4 minus 8 is -4, oh goody. Don't worry, this still works like it used to. It's still 2i, so -2 plus or minus 2i over 2. Everything is screaming to be reduced, but remember, you can't just reduce part of an addition or subtraction problem. It has to be all of it. Or alternatively, you could split it into 2 fractions and reduce them, Either way, you get -1 plus or minus I. Actually, I'm going to take the word remaining off of this because in the homework, it's not just going to ask for the remaining zeros at the end, it's going to ask you for all of them. So all of the zeros are -1/2, which we found first, -1 plus I, and -1 minus I. Now, why weren't these in my list of possible rational zeros? Because they're not rational, they're not even real. It takes a little use getting to this flow, but it's very predictable. Make a list. Run the numbers through synthetic division until 1 is equal to 0 for a remainder. Use the results to factor, and then continue solving. I get the feeling that was a pretty long video, like unusually long. Yeah, I thought so.